Welcome, 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 ladies and gentlemen, to another episode of Prometheus University. And this is the third part of our series on soil dynamics. Actually, it's the third part of our series on structural dynamics, of which we're taking a detour into soil dynamics. Yep, gotcha. Now, why are we going into soil dynamics? Well, that's because a important part of what we're trying to do is we're trying to design structures for earthquakes. What's another word for soil? That's earth. So we need to know the ground motion, the ground shaking, the dynamic properties of the ground, because it is that ground motion that is going to go into our building, cause our building to respond in ways which we care about. Respond in ways such as displacement, acceleration. Acceleration times the mass causes the forces. These forces and displacement result in stresses in the members, and we need to be able to design the members of this structure accordingly. So, in our typical fashion, let's go ahead and recap our previous videos. Let's go ahead and recap our previous videos. Now, in the first part, which I urge you to watch, we came up with the basic notion of how we relate natural frequency and stiffness. Natural frequency, stiffness, and mass in a simple spring model using the kinetics of the spring model, which have to do with acceleration and mass, and also the kinematics, which have to do with the displacement, velocity, acceleration, right? These space-time parameters, if you will. We combine these together, and now for any kind of structure for which we can talk about the mass and a stiffness, we can come up with the natural frequency, which is a very important dynamic property of the structure. That was video 1, episode 1 in the structural dynamics series. Part 2, we took the 1 degree of freedom scenario that we had in video 1, and we expanded it to multiple degrees of freedom. Multiple degrees of freedom. Consider the image to your right, such as a 3-story building. Each floor can move independently. Now we have 3 positions to describe, 3 independent positions, velocities, and acceleration in order to describe the motion/position of the structure. So coming up with the idea of degrees of freedom, which we formally define as the number of independent displacements that we need in order to describe the position/motion, right? The idea of modes then naturally flowed out. Modes and degrees of freedom go hand in hand. 1 degree of freedom structure only has 1 mode of vibration, right? 1 mode along that 1 degree. A multiple mode structure, as we see here, can vibrate in different modes, one of which is demonstrated by the masses snaking around in that red pattern as opposed to the 3 black masses which are straight up vertical to the left. We can see that that mode of vibration shown there, that serpentine mode, is one that can be resisted, one that can be performed, a particular dance that can be performed by this structure. So degrees of freedom and modes came into the picture, and we simply expanded the equation because now we just have more masses, more stiffnesses, and more modes, each of which has a natural frequency. So first video, coming up with natural frequency, relating it with stiffness and mass. Now we have more modes, more masses, and so on and so forth. And we just have a series of different vibrations with different natural frequencies which we can relate. So now our task, as we mentioned before, is to design a structure. We may be designing a structure in San Francisco, California, or we are designing a structure in Delhi, India. It could be in China. It could be in New York. It doesn't matter where it is. But if the ground motion, the earthquake characteristics of that site are sufficient, then we want to know, well, what kind of motion is our structure going to experience? What is the ground motion going to be like? And how is our structure going to react to that ground motion? Something about the natural frequency is going to be important about our structure, right? Perhaps we could have resonance, whereby the ground motion resonates with the natural frequency of our structure. Either way, we need a way of predicting at a particular site what the ground motion is. What do? Do we take ground motion measuring equipment and put them all over the earth and measure the motion? Even if we were to do that and we're able to record the motion and get the maximum velocity, maximum acceleration, and so on and so forth, how do we know that we're getting the data for the maximum or the worst kind of earthquake? We only have the data that we have recorded for the recorded motions. How about an earthquake that only happens once every 100 years? Once every 50 years? Do we wait for 100 years measuring before we build our structure? No, we don't do that. And the ways in which we are able to estimate and predict the ground motion on a particular site is what we're going to cover today so that we can design our structures accordingly. Again, the first two videos we come up with the model of the structure itself, its dynamic properties such as natural frequency, relating it with stiffness and mass and so on and so forth. Now we're getting into the input motion, which is the shaking of the ground. Now, we have maps that tell you, hey, here's this thing called spectral acceleration, measured in G's, right? Spectral acceleration. We are able to map out what this term is, which we'll get into in a second, on different sites. How did we go about doing this? As I said, we cannot just measure everywhere. And also, how do we change the magnitude of the earthquake, right? We can't just wait for the 100-year earthquake to happen in order for us to be able to make predictions. So how do we build this model? How do we build this model that predicts the spectral acceleration or spectral velocity or spectral displacement of the ground in different places? So let's get directly into this word then called spectral acceleration. If we look at, let's say, a document such as the ASCE7, American Society of Civil Engineers, which prescribes the means of calculating various loads, dev load, live load, snow load, earthquake load, so on and so forth. We're looking at an equation from chapter 13 here, which calculates the acceleration for a non-structural component like a HVAC unit or a duct, pipe, conduit, transformer, whatever it may be that's attached to a building. And the main thing that we're looking at there is that thing called the SDS. The SDS is a parameter in that equation over there on the numerator. And the SDS is a spectral acceleration. It is that thing which was mapped, which helps us to predict the motion of the ground, which we're going to get into today, albeit qualitatively. But we want to look at this particular spectral acceleration. What is it? How do we go about predicting when we didn't measure everywhere and we didn't measure all the magnitudes of earthquake? What are our different ways of modeling and then predicting? What are the parameters that affect the rate of shaking, if you will, at a particular site? Okay. First of all, let's try to wrap our heads around this thing called spectral acceleration. Now, spectral acceleration basically is defined here as SDS, right? Spectral acceleration of the design spectral acceleration, I should say, okay? It's 2/3 of SMS. What are those about? It doesn't really matter, okay? We're going to get into what the spectral acceleration is such that SDS and SMS and all the other S's become apparent to us, it becomes clear. So the spectral acceleration is defined like this. It is the response, this acceleration response, okay? It's important that we get this part. A spectral acceleration is the response, and response could be displacement, velocity, or acceleration. A spatial response of your structure due to an input motion. Due to an input ground motion in this case, how will a 1 degree of freedom with a particular frequency respond? So, as we know, we can model or build a particular structure with a particular frequency because we know that based on the stiffness and the mass, right, we can come up, say, well, the particular frequency, or let's say the period, right, the period is equal to the square root of the mass divided by the stiffness. So we have that, and we can come up with something like that for our structure, whether it be for the different modes, which we talked about in the second video, or for a single degree 1 modal structure, which we developed in the first video. We can come up with that. Now, the spectral acceleration or the spectral response, which is mapped in the map which we showed you before, is we take a 1 degree of freedom object and we go ahead and we shake it, okay? And we say, what is its response for various frequencies? How about if I make a structure, I model a structure with a frequency of, or let's call it a period of 1 second, period and frequency inverse of each other. Inverse, I should say. So what if I were to say 1 second, 2 seconds, 3 seconds? What is the response of that particular structure? That is what we're asking. That is what we're answering here today. So as we move forward, we're going to see how we come up with the ground motion. Because so far we already know how we model a single degree of freedom object, a 2 degree of freedom, 3 degree, and so on and so forth, the various modes relating it to stiffness and to mass using this inverted pendulum model, which relates to the spring model ultimately. But how do we come up with the ground motion for all the sites such that then we can map this thing called the spectral acceleration? So remember, the spectral acceleration is not just the motion of the ground. It is the response of a single degree of freedom, little lollipop that I show on top of there, single degree of freedom structure with a particular frequency, which we plot, to an input motion, right? And the input motion we need to know based on the soil dynamics, based on how far the earthquake fault is, based on the magnitude of the earthquake and all these other things. Hence, we're going to go down into the soil today for our brief detour in order to elaborate upon this particular aspect. Okay? So, now, as I mentioned before, there are maps for this. Let me go to the previous screen here. There are maps that map this thing out. But obviously, we did not measure we did not measure, take a vibration measuring device and place it everywhere. And how do we vary the magnitudes and all these kinds of things? Obviously, we created an analytical model of this natural phenomenon using certain parameters, as we usually do, right? So the parameters that would affect how the ground shakes, right, are what we are talking about. So there are two ways of going about predicting what kind of shaking is going to occur at your site. You're building a structure, what kind of shaking is going to occur at that site. We have the deterministic seismic hazard analysis called DSHA, or the probabilistic seismic hazard analysis. The maps that I showed you previously are called seismic hazard maps. The seismic hazard maps, as we said, has plotted spectral responses, which could be positions or displacements, that is, displacements, velocities, accelerations, okay, which are the responses, the displacement response, the velocity response, and the acceleration response of a single degree of freedom object on that site. Okay? Now, the basic idea of deterministic, it just means that it does not include the probability of that earthquake happening, does not include any kind of statistical data. So it's deterministic. It just gives you a maximum acceleration. It says for this site, this is the maximum acceleration that your single degree of freedom structure with a particular period is going to experience. It doesn't tell you the probability that it will experience that. That is the probabilistic seismic hazard analysis, which we'll talk about in the next video. But the idea is still the same. One just gives you, here is for a given magnitude and some certain other parameters for this site. Well, here is the acceleration you're going to experience. So we are simply going to talk about in a qualitative way, now that we've understood that soil dynamics or earth dynamics are very important for structural dynamics, generally speaking. We are going to then in a qualitative way explore some of the parameters that we understand will affect how the ground shakes. Okay, so one that we can immediately come up with is, well, the distance from your site to the fault, right? In other words, you have to pick a fault, right? Pick a particular earthquake fault. a fault that can generate an earthquake, okay? And you pick that one, you get certain parameters, and you come up with a number for that one, and then you pick all the other surrounding ones in this kind of deterministic way, and then you make a decision as to what the worst case scenario is, and so on and so forth. Now, there are several kinds of distances. This is just for us to get used to certain kinds of nomenclature and so on and so forth. But we're still just thinking in a very conceptual way. We're not going to get numeric with our soil dynamics, but I think that soil dynamics and the understanding of that term, spectral acceleration, is very important. How did these maps come up such that we can predict the response of our structure that we're going to build here in San Francisco, in Beijing, in Delhi, India, in New York, wherever it may be? How are we able to come up with this? Okay, cool. You have your site and you know how far it is from a particular fault, right? Okay. There is the epicenter, which is the distance on the earth, as it's shown over here in this diagram, right here, okay? The distance on the earth, on the ground surface, from where the earthquake actually happened, okay? Above ground, that distance there, where the earthquake was measured, right? Where's that epicenter, right? And then that distance is, called the epicentral distance. And then you also have the hypocentral distance. The hypocenter is the actual location of the earthquake, of the rupture, of the shaking, right? Where the fault moved. So there is another distance, right? Which is R5 here, the shortest distance. So the point here is we're thinking qualitatively that, okay, how is this house over there going to shake at the site? And what is it depending on? It's going to depend, I think, so the saying goes, right? When you're coming up with the parameters to come up with this equation, you will not be wrong to think that it depends on the distance to the earthquake, to the source, which is the fault. The type of fault also matters. But all these pieces of data are gathered for many different sites in order to come up with different models and so on and so forth. Well, we talked about these different distances and the type of the fault. What else matters, though? What else matters? Well, let's look at an example and let's just talk qualitatively about a model. This is called Campbell attenuation relationship. Basically meaning it tells you, well, for a given magnitude of earthquake, along with certain other parameters such as distances and so on and so forth, what is the acceleration? Okay, what is the acceleration? What is the spectral acceleration at my site? What is the floor acceleration, sorry? And then when you get the floor, the ground acceleration, then you're going to model on top of that your single degree of freedom structure with a particular frequency, and then you plot the spectral acceleration for that site relative to frequencies, okay? So we have several frequencies that we can model or build, which again are based on the mass and the stiffness. And then the frequency will affect the way that the structure responds. That makes sense, right? So I'm at this particular site. The floor shakes. Well, the structure will react based on its dynamic properties, one of which is its natural frequency or its period, its natural period, right? So we plot for different periods this spectral response, which is the response of the structure from the ground motion. Now, I keep repeating this because it is very important. It's very important kind of verbiage for structural engineers to understand, and engineers generally to understand how the soil dynamics goes into the structural dynamics in terms of how we model it and what that map actually means, what the spectral acceleration means, because a lot of people seem to think that the spectral acceleration that is mapped is actually the acceleration of the floor. No, it is the acceleration of a single degree of freedom model with a particular period. So the map will tell you that the period, in other words, period being the inverse of frequency, the natural period of the structure, the map will tell you this is for period of 0.2 seconds, 1 second, so on and so forth. Okay, so if we look at this particular example, it says, hey, ln of omega max, and omega max is the maximum acceleration as defined over here. The maximum ground acceleration is what we're looking for. Again, the maximum ground acceleration is what we are looking for. And that maximum ground acceleration can be determined based on the moment magnitude of the earthquake. In other words, what is the magnitude of the earthquake in terms of you decide that? You say this fault has been known or can produce such and such magnitude of earthquake. What then will my structure experience if I'm at this site? Based on our distance from the source, right? A certain distance from the source is a parameter which is here, which makes sense to us, right? And then we have things such as the rupture strength of the rock and the rupture area and the displacement, which multiplied together is called the seismic moment, right? But basically, the strength, the energy that is put out by the fault. The energy that is put out by the fault is going to be important. The kind of properties in terms of whether it be a stiff soil or a non-stiff soil is going to affect the way the loads are attenuated or amplified, right? So this, again, is a rather qualitative overview of the thing that matters to us when we're trying to figure out how a particular site shakes, because we're not going to measure the shaking of every site for every magnitude of earthquake, even those that only occur every 100 years. Okay? So basically, the cyclic behavior, okay, the dynamic behavior of the soil is going to be very important, because when Campbell came up with his model, right, and all these other models that are out there that say, hey, you're on a particular site, what happens over here when that particular fault has an earthquake of this magnitude? Again, you are at a particular site. What happens when that fault over there has an earthquake of this particular magnitude? Well, how far am I away from the fault? What kind of fault is it? How much energy can it produce? So on and so forth. Also, what is the media by which the vibration is transferred, right? What is the soil like? Is it stiff? Is it not stiff? So on and so forth. As we can imagine, very intuitively, these things are going to be important as well, so that we can predict, again, what we're trying to do here, ladies and gentlemen. What are we trying to do? We're trying to build a building at a site, and we want to say, I need to be able to predict the kind of response in terms of position, velocity, acceleration that the structure will have, because this acceleration of the mass and the displacements will cause stresses in the structure, and we want those stresses to be resisted. Okay, so what are some soil dynamic properties, and how do we measure them is how we're going to close this out, and when we're going to give a recap. Again, we're keeping this rather qualitative, okay, because we're not going to go deep into the geotechnical aspects of it. We're just talking about, we're taking this journey down the lane of structural dynamics. We have gone from a single degree of freedom structure to a multimodal structure, multiple degrees of freedom. But let's take a stop and let's ask ourselves, where does this earthquake come from? Because the earthquake is an important part of the input motion that we're going to put into our structure, see how it responds, and so on and so forth. So we have the elastic modulus and the shear modulus, the Poisson ratio, something called the shear wave velocity, which we actually measure at the site. And the density, of course, would also matter. In other words, these things which we can imagine, which we can understand, that in a certain sense speak to the stiffness of the soil itself, is going to affect the way in which the soil shakes. Similarly to how we related the stiffness and the mass of a single degree of freedom object to its natural frequency, using the spring model in the first video in this series, the structural dynamic series, that is. So these, along with other damping and attenuation parameters, okay, are going to affect the way the soil behaves, okay, at a particular site. And these are the different factors that come into play when we determine how our structure is going to behave at that site, okay? And again, as I said, let's go back, okay? Let's go back, and this particular data is mapped Okay, it is mapped. What we're asking ourselves is, how is this map determined? And we're asking ourselves, what does this map show? We say that the map shows a spectral acceleration, okay? But the spectral acceleration is not the acceleration of the floor. It's the acceleration of a single degree of freedom little pendulum that you have on top of the floor that represents your structure, and that you're going to use that to model how your structure is going to behave. I have a particular single degree of freedom model with a particular period. And based on the shaking of the ground, what is the maximum acceleration of that thing? I can know stiffness and the mass. I can model something to get all kinds of natural frequencies. But what is the shaking of the floor? So we come up with models that describe basically how this flows, So we have said things such as the distance, things such as the fault, how much energy can the fault put out, and so on and so forth, very important. And a Campbell model here, just an example of a deterministic way. And in the next video, we'll get into the probabilistic way. The probabilistic way just adds an extra dimension that also tells you the chances of that particular earthquake occurring within a time period. So say there's a 5% chance of this acceleration being experienced at this site for the next 50 years. Something like that, right? The deterministic, which we're looking at right now, just gives you a number over here, which says the maximum ground acceleration, or the logarithm of the maximum ground acceleration, and then you can convert to just the maximum ground acceleration without the logarithm. Just gives you that number for this particular pieces of input. How far from the site, what's the magnitude of the earthquake, what's the energy that is put out measured in the seismic moment, and so on and so forth. So now we looked at some seismic, or shall we say some soil dynamic properties, okay? And let's just say a little bit about how they're measured, okay? We have some in situ tests that are done, okay, that basically kind of measure the reaction. You know, you have a source of vibration, and then you have a receptor, if you will, on the other side, right? A receiver, a sensor, and you measure, okay, the shear wave velocity and other kinds of soil dynamic parameters in order for you to understand the medium that transmits that vibration from the fault to your site, right? Because that's going to be quite important. So there are various kinds of in situ tests that are done, and various kinds of measurements of different kinds of magnitudes that are done. And together with all this complex information is gathered together, and different people create different models. As we can understand, this is not going to be a simple thing. What are the parameters that you should use? What is the functional form that you should have? Should it be a linear equation? Should it be a polynomial, or should it be a logarithmic equation, right? In other words, the functional form is important. How many parameters do I have to include? Do I include barometric pressure of the atmosphere? How much does that affect the shaking of the ground? I'm sure it affects it some, but is it enough for me to put that in my equation, right? Or is it negligible? In other words, people come up with models taking into account all these different factors, some of which are intuitive to us, others of which need to be dug into a little deeper. And also, with more data that is collected over time, we can update these models, right? These models, such as the Campbell equation that says, hey, if you have a particular distance from a site, from a source, okay, and you have a particular magnitude of earthquake, which you're trying to test for, and all these other little pieces of information, I can predict to you the acceleration, okay? That is the basic idea here. So, ladies and gentlemen, we did today something which we've never done before, which we went ahead and we trying out a live video. We are trying out a live video for the first time. It is partially in an attempt to go ahead and increase the output, if you will, increase the outflow, increase the manner in which we're able to put out content on this channel. So that is partially why we've done this. Ladies and gentlemen, perhaps in future episodes of the lives, we'll go ahead and make it more interactive. We can ask questions, give answers, and so on and so forth. But for now, let me go ahead and try to give a basic recap of where we are at and what we have done so far in our series on structural dynamics. Okay? Yes. Coming up with a single degree of freedom model, relating the mass and the stiffness to the natural frequency. Coming up with the concepts that expands the equation into a series of linear equations, and then we bring out matrix algebra in order to solve many degrees of freedom and many modes, which means now we're going to have many natural frequencies depending on the mode of vibration and so on and so forth. That was the second video. Then we're talking about building a particular structure somewhere. And how do we know the kind of vibration it's going to experience based on earthquakes? So we take a detour into some basics of soil dynamics, and there's something called the spectral acceleration. It's a very important aspect of solving or coming up with the acceleration that your structure is going to feel. And that is based on the response, a displacement response, velocity response, or an acceleration response, all these space-time responses of a single degree of freedom structure with a particular period to a particular input motion. Okay? Input ground motion right here. But how do we know the input ground motion? And then we talk about how these different models exist, of which one is deterministic, and it takes into account how far from the source are you. Vertical distance, shortest distance to the source, epicentral distance, hypocentral distance, right? What kind of fault is it? What kind of source is it? Is it one that can generate a certain amount of magnitude based on of earthquake? And what exactly are the dynamic properties of the soil and the rock around? All these will greatly affect how your site accelerates. So that is the extent of our video, ladies and gentlemen. Today, I wanted to make a quick one, and we will be continuing with this mode of going live, putting out the video in an extemporaneous manner so that we can put out more content. So next time we'll be talking about the probabilistic seismic hazard analysis, or PSHA, which basically adds the idea of the probability of a particular earthquake or a particular acceleration, a particular spectral response, right, occurring within a particular time frame. Thank you very much. Go ahead and like, share, and subscribe if you indeed enjoyed this video. Until next time, be safe.